So yesterday we had a brief introductory into energy and what kinds of energy, the different types of energy we have, like kinetic energy for motion, gravitational potential energy, and so forth and so forth. Today I'm going to introduce you to the concept of work. Okay, so work has a specific meaning in physics. It's not the same as when we use work in the English language. So we say work is done in an object when a force displaces the object in the direction or a part of the direction of that force. Okay, so for example, if you're lifting a heavy box, right, it may seem very heavy. You may start breaking into a sweat, whatever, but you're not doing any work on the box if you're not moving it, right? If you're just holding it there. It may feel like you're doing work because you're exerting a lot of force on it, so you're getting tired and you're using up your own energy, but you're not doing any work on it. You have to move it. Okay, so for example, in this case, right, here we have somebody pulling a bunch of grocery carts. So in this case, you're pulling them, so you're applying a force and they're moving in that direction. Right, so you have both displacement and a force which has a component in that direction of displacement, so you're doing work. Okay, so work, in other words, is proportional to force, or at least the force that's in that direction. It's also proportional to displacement. What those means is, this means the more force I apply, the more work I'm doing. The greater the displacement of the object that I'm moving, the more work I'm doing. Written as an equation, we write it as force equals force times displacement. Okay. Now in this case, it does matter the direction of force and displacement, but for this course, we're just going to assume that they're both pointing in the same direction. Well, actually, we're going to look at three special cases. The first special case is when they are both pointing in the same direction. Now, what work does is it actually either gives or removes energy from the system. So, for example, if I have a textbook right here, right, currently it has no motion and therefore no kinetic energy, but if I apply a force and I move it in that direction, so there's a displacement, you can see that now it's motion. It has kinetic energy. My work gave energy to that book. So there's a very deep connection between force, work, and energy. And work is actually a scalar quantity, just like energy, and it has the same units as energy, right? Joules. So you measure work in joules. So let's go over an example problem. Here's our first example. So we have a curler that does 210 joules of work. So let's write our given. Work equals 210 joules on a curling stone as it moves 14 meters. So that's our displacement, 14 meters. Assuming that the ice surface is level and frictionless, so we're going to ignore friction for now, how much force does the curler apply? Okay, well here's our equation up here. Work equals force times distance. And if it helps, you could make a triangle for that, because we're not actually solving for work in this question. We have work, force, and distance. So in this case, we're solving for force. So force is going to equal work divided by that distance. So force equals work divided by that distance. So now we're going to plug in our known values. So 210 joules divided by 14 meters. Okay, and joules per meter is newtons. We get 15 newtons. Alright, so I said we're going to go over some special cases. The first one is actually one that we just did. So on the example we just did with the curler, we're doing positive work. So positive work happens when you have both force and displacement pointing in the same direction. And that tends to increase the speed of the object, therefore increasing the amount of energy that object has. Okay, but there is negative work. So you have negative work acting on an object. What negative work is when you have force, that vector force, and the displacement vector in opposite directions. So a common example would be friction. Friction does negative work. You saw when I pushed the textbook, right? Originally I gave it energy, but then it came to a stop. So it lost that energy. How did it lose that energy? Friction did negative work. And negative work removes energy from that system. Positive work can add it, negative work removes that energy from the system. So let's try an example with negative work. Okay, so question number 2. This one we have a toboggan carrying several children, so we have a total mass, reaches its maximum speed at the bottom of the hill. So it's sort of slid down a hill, and right at the bottom it's at its maximum speed. Then glides 20 meters along a horizontal surface before coming to a stop. Okay, that's right, what we know so far. Mass is 100 kilograms, and we move a displacement of 20 meters before coming to a stop, meaning our final velocity would be 0. Coefficient of kinetic friction between the toboggan and the snow is 0.1. Okay, so this is sort of having us sort of recall what we did in our forces unit. So let's start with a free body diagram. There's our toboggan with the children on it. We're going to have force of gravity. We're going to have that normal force. And if we're moving in this direction, there's going to be a frictional force, specifically kinetic frictional force, in the opposite direction, opposing motion. Alright, so there's our free body diagram. It says determine the kinetic friction. Well, we have a formula for that. Kinetic friction is mu Fn. They give us mu, right? 0.10. But we need Fn. Now, if you remember in this case, right, it's just on a horizontal surface. Fn is equal and opposite to Fg. And to calculate Fg, it's just mg, where g is 9.8 newtons per kilogram. So this is going to be mu mg, which is 0.1 times our mass, 100 kilograms, times g, 9.8 newtons per kilogram. So that gives us 98 newtons. So there's our frictional force. Now C says calculate the work done by kinetic friction. Well, the work done, in this case, is going to be negative. Right? And that you'll have to determine on your own, but you just have to remember that if our displacement is in one direction, and our force that is doing the work is in the opposite direction, you have negative work. Okay? And it's negative force, the magnitude of that kinetic friction, times displacement. So we have minus 98 newtons times our displacement, which was 20 meters. So that gives us, sort of ran out of room, minus 1,960 joules. So I'll just pause it there. Alright, so we looked at, say, pushing something horizontally and having friction oppose it, but you can also have gravity oppose. So let's say I'm lifting something up. Okay, in this case, my applied force is up and the displacement is up. I am doing positive work. However, if I'm lifting it down, my applied force is up, but displacement is down. So in this case, I'm doing negative work. Okay, and be very careful with work because work is always done by a certain force. You can actually look at concepts like total work, which would be the net force, the work that a person does, which is the applied force. You can also consider the work that gravity does, for example. Right? If I lift this book up, I may be doing positive work, but gravity is doing negative work. Okay? So whenever you're doing questions based on work, always ask yourself, okay, what's doing the work in this question? So let's try the next question. Question number 3. Here you have a bag of groceries of mass 8.1 kilograms is raised vertically upwards without acceleration, a distance of 92 centimeters. So let's write what we know. So we know the mass, 8.1 kilograms. We know the distance, but we need to change that into meters to have proper SI units. So that would be 0.92 meters. Right? Determine the force needed to raise the bag without acceleration. So to raise something without acceleration, you need to be providing an upwards force that is equal but opposite to the downwards force. In this case, the downward force is gravity. So we would need to calculate what that gravitational force is, which would be mass times that gravitational field strength, 9.8. So we have 8.1 kilograms times 9.8 newtons per kilogram. And you get 79.38 newtons. Now technically, I would just write 79 newtons, rounding off to 2 significant digits. But since I'm going to use this result in my next question, I'm just going to leave that there for now. Part B says the work done on the bag of groceries against the force of gravity. So the work that we do against the force of gravity. Right? So we're lifting it upwards, and so we're applying an upwards force. That's positive work. And we can calculate it by looking at that force, which we must apply to oppose gravity, multiplied by the distance that we raise the bag. And so we have 79.38 newtons times by 0.92 meters, and we get 73 joules. Now I did put it into 2 significant digits. Okay? Just pause it there. All right, so the third special case that I'm going to talk about is zero work. So we had positive work, meaning our forces are in the same direction as displacement. We had negative work when force and displacement were in opposite directions. Zero work is when force and displacement are perpendicular to each other. So an example of this would be, again, I'll hold my textbook. So I'm applying an upwards force, but I'm moving in this direction, or in this direction. It doesn't matter. Those displacements are perpendicular to the force I'm applying. So I am actually doing no work. So that's the case of zero work. Okay. Same thing here. If you have, say, an air hockey table and you have a puck there, okay, let's say you have the air pushing upwards on the puck. But if the puck's moving horizontal, the air is really doing no work on the puck, because those are in 90-degree directions. Okay, a skater that's gliding on the ice. Okay, again, in this case, you have someone lifting someone else up, obviously applying a force, but moving perpendicular to that. Okay, I mean, there's other cases where you can have zero work. You can go up and say push against the wall. you may be applying a force, but in that case there is no displacement. So that's another case where you'd have zero work. All right, last thing I want to mention is if you were to have a force displacement graph, so here's your force on your y-axis and your displacement on your x-axis, you can find the work done by finding the area under that force displacement graph. Okay, so whether or not you apply a constant force or a constant force and then a force in the negative direction, giving you negative work, or if the force you're applying is changing. Now this is important. If the force you're applying is changing, you cannot simply use the equation and say F times D. Because using the equation saying F times D, that's this example. Right? You're finding this area for a constant force. But if your force is not constant, well, you'd have to find the area under that graph. In this case, we have a triangle, so it would be 1/2 F, your height, times D, your base. Okay, which that is really finding the average force. Okay, so let's try our last question now. I'm going to zoom in on this one a bit. So this one says calculate the total work done in the graph below. So first we have a constant force, okay, and then our force decreases and then becomes negative. So let's break this problem up into 3 parts, A, B, and C. We just need to find the area under the graph for A, B, and C. So for A, let's say the work done for that A portion would be the area of a rectangle, right, which is just length times width. So in this case, 5 newtons times 2 meters. So 5 times 2 gives us 10 joules. All right, for B, and now we want to sort of find this area in here. So that's a triangle. The area of your triangle is 1/2 base times height, where in this case would be bases between 2 and 3, so 1, and your height is 5. So 1 times 5, 1/2, 1 meters times 5 newtons, gives you 2.5 joules. Your last one right here, this is negative work. Right? It's also a triangle. So we have 1/2 base times height. It's going to be negative, and you can see on here also why, because we have a negative force being applied in the opposite direction. And so we have 1/2 times our height, which is negative 5 newtons, times our base, which goes from 3 to 4, so that's 1 meter. This gives us negative 2.5 joules. Now to calculate the total work, we would just add all the work together. So 10 plus 2.5 minus 2.5 just gives us